Today, we want to present about the regenerative ranking cycle. So, the figures show DTS diagram for ideal ranking cycle that we have 4 steps involved. Step number 1, step number 2, step number 3, and step number 4. Okay, so this is the DTS diagram for ideal ranking cycle. That we add one more point, step number 1 prime, that discuss linear relative cycle. We can increase the terminal efficiency ranking cycle if we get increase the average T during heat addition process of the boiler. So, if we can increase T average of the boiler, the thermal efficiency for the relative ranking cycle also will increase. So now the process will involve state number 2 until state number 3. When during the process liquid water enter the boiler and heat addition will occur the end of heat addition process. The boiler will steam exit the boiler and enter the turbine. So, if we look during the process, the heat transfer is at relatively low temperature, which is go to the process involves step number 2 to step number 2 prime. So, this process we consider as low temperature heat addition. T average during heat addition process reduce, and this condition will cause lower value of thermal efficiency during Rankine cycle. So the method that we can use to increase the temperature of T2 we call regeneration process, where we need to supply heat. So we need provide that heat transfer to feed water that supply to the boiler. So if we can increase the temperature of heat water that refer to T2, so the value of T average during heat addition process will increase, and the thermal efficiency for Rankine cycle will also increase. So now for the solution 1 for regeneration and how to transfer heat water. So the first solution is expanding steam in a counterflow heat exchanger built into the turbine and show in this diagram. And however, his method not practical. Why? Because is it difficult to design, and final stage of turbine will have lower value of steam quality. Then we have second solution to solve this problem. So for the solution number 2, we can supply heat transfer to heat water to another increased temperature, water T2, by extracting steam from the turbine at various points that show in this diagram. So the advantage for deaerating, remove air at initial stage to prevent corrosion. Regenerative ranking have 2 steps, which is open feed water heater and another one closed feed water heater. So we discuss about ideal regenerative ranking cycle with open feed water heater, that also called OFWH. So this regenerative diagram for open feed water heater that we have 2 pump number 1 and pump number 2, 1 boiler, 1 turbine, and initial stage to go through open feed water heater, and their liquid for condensation will enter pump number 1. So open feed water heater actually is missing chamber, and the vapor will have direct control during process where the liquid from pump number 1 will enter the open feed water heater and mix with the steam from the turbine exit. And this case will face the water will be called saturated liquid. And next, the slide shows TS diagram for ideal regenerative Rankine cycle. Okay. So we have step number 1 that calls saturated liquid. Then step number 2 will be compressed liquid. Step number 3 will be saturated liquid, and step number 4 will be outlet pump number 2. And the process will be isotropic process for pump number 2. Okay, in term analysis, for heat transfer, so Q in the value of heat addition process in the boiler that show in diagram, also TS diagram. The formula will be Q in equal H5 minus H4. The next value of Q out equally 1 minus Y multiply H7 minus H1. Next, work isentropic. We have two pumps, so we need to consider W pump total also equal to 1 minus Y multiply Y W pump 1 plus W pump 2. So the total W pump total also equal to 1 minus Y multiply W in 1 plus W in 2. Next, W in 1 equal V1 multiply P2 minus P1 equal H2 minus H1. Next, W in 2 equal V3 multiply P4 minus P3 equal H4 minus H3. For W turbine, equally W out equal H5 minus H6 plus 1 minus Y multiply H6 minus H7. So for steam fraction per mass, at the boiler we consider be 1 kilogram of steam, and for turbine exit at 0.6, steam fraction per unit mass will be Y. At 0.7 will be 1 minus Y. Next, we discuss about actual regenerative Rankine cycle with open feed water heater OFWH. So this is a schematic diagram for ideal and also actual regenerative cycle will be same. And now for actual regenerative Rankine cycle, we need to consider pressure drop, temperature drop, and isentropic efficiency for the pump and also the turbine. So the efficiency not equal 100%. So this is the TS diagram for actual regenerative Rankine cycle. So if we look at TS diagram, we have 6 constant pressure line, 1, 2, 3, 4, 5, and also 6. We compare to ideal or that we have 3 constant pressure line because we need to consider temperature drop and pressure drop. So we have 6 constant pressure line. In terms of analysis heat transfer process, Q in formula will be H5 minus H4A, and for Q out equal 1 minus Y multiply H7. In terms of work, for W pump total equal 1 minus Y multiply W pump 1 plus W pump 2 also equal 1 minus Y multiply W in 1 plus W in 2. So for individual formula will be W in 1 equal H2A minus H1. W in 2 equal H4A minus H3. For W turbine equal W out equal H5 minus H6A plus 1 minus Y multiply H6A minus H7A. Next, we have example 4.4. Consider a steam power plant operating on the ideal regenerative Rankine cycle with one open feedwater heater. Steam enters the turbine at 15 megapascal and 600 Celsius and it condenses in the condenser at a pressure of 10 kilopascal. Some steam leaves the turbine at a pressure of 1.2 megapascal and enters the open feedwater heater. Determine the fraction of steam extracted from the turbine and the thermal efficiency of the cycle. So from the question, we need to calculate value of Y and also the thermal efficiency of cycle. First, we need to draw schematic diagram that have two pump number 1 and also pump number 2, one boiler, one turbine and also one condenser. And also we need to draw the TS diagram for ideal regenerative Rankine cycle. So we have step number 1, step number 2, step number 3, step number 4 and step number 5 and also step number 6 and then step number 7. So we have step number 1 10 kilopascal, step number 2 1.2 megapascal, step number 3 1.2 megapascal, step number 4 15 megapascal, step number 5 also 15 megapascal at temperature 600 Celsius and step number 6 also 1.2 megapascal. P6, P2, P3 that we know the pressure in the in term of inlet also outlet for upper water heater will be equal. And the last one, we have step number 7, 10 kilopascal due to constant pressure heat rejection process in the condense. Then for the TS diagram, we have step number 1, number 2, step number 3, step number 4, step number 5 obviously superheated, step number 6 and then step number 7. So now we need to determine the value of steam fraction that called W6 and also we need to determine thermal efficiency for the ideal regenerative Rankine cycle. And for the next, I pass to my friends Irfan to continue to present for you guys. Thank you.